we've just had a look at these, doing the electron configurations for these, and they do show us some different things when we write them. So, could I just have someone walk me through boron's electron configuration, please? Any one of us?
1 versus
1s2.
2s2.
Cool, and therefore it must be 2p1 because it's number 5. Notice that we haven't moved the 2s electrons into the 2p orbital to give that maximum spin. We're not allowed to do that. It can only be dropping an energy level. Okay, so 4s into 3d, for example. These are at the same energy level, as it were, so we can't move them. We could, with natural light, move them around a little bit, which will give it a colour, or we could do it with heat. We could burn it, and it might move from one of the electrons from the S into the P, but then it would return emitting light. Okay, so go to excited state. So this is just to show you, the reason I gave you this one is just to quickly show you that you must fill the S orbital before you start filling the P of the same energy level. Okay, and the energy level is shown by the big number. Okay, bromine. Please start me with argon though.
Argon.
Yep.
4s2.
4s2.
3d10. 4p5.
Fantastic. And the key thing I was trying to show you there is, even though we've got a 3 in between, well, you might have put it there, we're filling the 4th energy level primarily in our 4th period. Okay? Common error is for people to put 3p5 there. Really common error, so just be aware of that. Clearly shows it's got a valency of 1. By the way, these 3d electrons will not be involved in bonding necessarily because they are now a full energy level. And going by Hundt's rule, that is our optimum of stability. We've got full energy levels here. But we do have an incomplete, that's not a word, an incomplete orbital here, the 4p, which is why bromine will react and has a valency of 1. This is incomplete. All right, so this is showing me the 3rd energy level is now complete because it's got 3d10. That's complete. Okay, copper. Again, we'll start with argon. And I know I saw you guys working on this. We won't have it excited for that. No, the asterisk wasn't show excited. The asterisk was to show that we were applying Hundt's rule. So,
4s1.
4s1.
3d10.
Cool. Okay. This again is applying Hundt's rule. It's completed an energy level, and the sacrifice for doing that has only been to half fill an orbital. That's still quite stable. It's a half filled orbital. You couldn't drop both of those electrons and have it stable, by the way. So, for example, nickel, it has to have its 4s2 3d8. You can't drop both of them down for nickel. Okay, that's one I forgot to give you. So there we go. This is showing Hundt's rule because we've got maximum spin here. I know it's only 1 electron, but you've got a half-filled orbital, so that's stable. And this is super stable because it's a full energy level. Okay? 3rd energy level is full.
With how you use nickel,
Yeah.
would it be like more stable if you hit one of the
Just moved one of them down, so it's 4s1 3d9.
yeah.
No, it won't. That'll be less stable because 4s2 is a full orbital, which is more stable than what you'd be creating. Okay, so it goes most stable is a full energy level. I shall write that because that's what I was wanting to get to in this video. So you've got full energy level. Then you've got full orbital. Then you've got a half full orbital. Whoops. And that we describe as maximum spin. And then way down, you've got a partially filled orbital. So for example, 4 electrons in P, where you've got one up, one down, and the other 2 are up, that sort of thing. Okay, and that'd be way, way down. These are your 3 most stable arrangements in order.
So your priority would be try and get a full E level, but if you can't get that, get a full orbital.
Yeah, and so long as it's not at the sacrifice of having one of these 2. As long as it's not at the sacrifice of that. Okay. Copper's not sacrificing it because we still have that. We've lost that, the full orbital, the 4s2, but we've still got that, so it's okay. But if we fully sacrifice that orbital, we're not allowed to do it. Manganese, another good one to show. Argon. Then we've got,
S2.
cool, 3d, 5, great. So this is a very stable element because it's got a half-filled orbital in it. Okay, it's also got a full orbital in it. So its valence electrons, its outermost electrons, are in two very stable arrangements there. Okay, this will also help us explain the different oxidation states of manganese later in the unit. Okay, and the last but not least, sort of to show a bit of a pattern with stability here, nitrogen.
1s2.
Cool.
2s2.
Yep.
2p3.
Cool. Okay, and again we can see a half-filled orbital there, which is quite a stable arrangement. Okay, so the idea here was just to explore hints a little bit more, which is why I gave you those examples there.